So the difference between them is just, the type of equation that you have. In the first case, 8.1, we have a function defined in X or in Y. And in the second section, it's going to be a parameter curve defined in terms of the parameter T that we've seen, at the beginning of the semester. And in the third case, we use the polar curve, which is defined in terms of theta. And for all of them, we will be interested in calculating the length of one portion of the curve. And tomorrow, we will be focusing on the surface area in 3 dimensions. And the surface area is obtained after rotating a curve about the x-axis or the y-axis. You guys remember when you rotate and volume, when you rotate not volume, but when you rotate the area, so you will get a volume. That's what we did before. But when you rotate just, the curve, so you will get a surface area. And such a surface area, what we call surface of revolution. So we'll see tomorrow how to calculate them. In a case of X, Y coordinates in section 8.2, and also in a case of parametric curve in section 10.2. And as I mentioned, we'll cover these 3 sections today, 8.1, 10.2, 10.4, and tomorrow, so we'll cover 8.2 and 10.2. And next week, so we'll do, some review questions. I'm gonna post, this weekend some past final exams to practice, and I'll solve, some of them, in our class next week. All right, so now let's see how to calculate the arc length by using a definite integral. And to do so, I'm just gonna consider this function, which is defined by y equal to f of x. The function here is defined in terms of x, and it's the curve, the red curve here. This is my function y equal to f of x. It means the function is in terms of x. And now I'm interested in calculating the length of the portion of the curve of f joining the point A, capital A, and the point capital B. So exactly what I'm want to calculate is this portion here. And to do so, what I'm going to do is I'm going to split it into small portions and calculate each of them. And at the end, I'm going to just, add up all these terms. And to do so, I'm going to start by the first endpoint here, which is A. I'm going to just call it P0 for the first point. And I'm going to name, its x coordinate here. I'm going to call it x0 or x0. And the value C here, I'm going to name it y0. I'm going to choose another point. Let's say here, I'm going to name it P1. And x coordinate going to be here. I'm going to call it x1. And y coordinate, I'm going to call it P1, y1. And so on. Let's say for P3, I'm going to take it here, P2, the third point. Its coordinate, I'm going to call it x2. And its y coordinate, I'm going to call it y2, and so on. I'm going to repeat this process, until the last endpoint. I'm going to just add all these points. Okay, as I told at the beginning, I'm going to split it in small portions, and I'm going to add all the length of all these small portions. And let's say the last endpoint, which is equal to capital B, I'm going to call it Pn. So in fact, in this case, I subdivide the curve or the portion of this curve joining A and B. I subdivide it into n portions. That's why I have just n plus 1 point. So from 0, P0 to n, I'll get n plus 1 point. And P, I'm going to call it xn, the x coordinate of the last point and the y coordinate, I'm going to call it here the d, I'm going to call it yn. So basically what I did is for all I, okay, I going from 0 to 1, so I is the index of the point, I is going from 1 2 3 up to n. I create my pi, the point p, and with coordinate xi and yi. And you guys can see here when I is equal to 0, point gonna p0 with coordinate x0 and y0. When y equal to 1, I equal to 1. So you'll get the point p1 with coordinate x1 and y1. The index I equal to 2, you will get point p2 equal to x2, y2, and so on, up to I equal to n, you will get the n plus 1 point. Pn gonna be xn and yn. Okay, now this the gap between, for example, here x0 and x1. This distance I'm gonna call it dx1. The second one I'm gonna call it dx2. So you guys have to take, you know, this picture, the graph, because we're gonna use it. I'm gonna explain more the details, you know, each step and so on. And the gap between y1 and y0, I'm gonna call it dy1. Distance between y0 and y1. Between y1 and y2, I'm gonna call it dy2, and so on. Okay, and dli gonna be, for example, I'm gonna call dli the length of the curve of the portion of this curve joining pi minus 1 and pi of the curve of f joining pi minus 1 and pi. So joining these 2 points, p, because I already know my pi minus 1, and the point, which is pi. Just keep in mind, pi and pi minus 1 are 2 consecutive points. And this for all I from 1 to n. So basically it means when I equal to 1, you replace here I by 1, you will get p0 and p1, and here's dl1. So it means dl1 is the length of the curve joining p0 and p1. So it means this portion here between p0 and p1, this is what I call dl1. The portion joining 1 and p2, this is, you know, what I call dl2, and so on. Now I'm gonna approximate, you know, these values. Let's say how to approximate it. I'm just gonna change the color. So to approximate, I wanna calculate this DLI, the approximation. Okay, I'm gonna create a rectangle. The green rectangle. And you guys can see here, the hypotenuse is really close to the length of the curve joining P1 and P2. That's why we're gonna take the hypotenuse as an approximation of the of the portion of the curve joining P1 and P2. And to calculate the hypotenuse, I have to use the theorem. And to do so, you guys know the opposite side here. The opposite side is what I call DL2. And the adjacent side is what I call DX2. So DL1, which is the length of this curve joining P1 and P2, is approximately equal to the hypotenuse. But the hypotenuse, when it's squared here, gonna be dxi u squared. And just keep in mind, dxi is the adjacent side of the right triangle. You add here the opposite side of the right triangle. Pythagoras theorem. And you guys can see it here. And DLI is not the hypotenuse, be careful. I is exactly what I want to calculate. I defined it here, but I'm going to approximate it by using the hypotenuse because they are really close. If P1 is really close to P2, you know, the DLI going to be really close to the hypotenuse. And this is exactly what I'm gonna give the details on the next slide. And it means here, so what I did here is just for the second interval, x1, x2, I'm gonna repeat it for all what I did for the second interval here, I'm gonna do it for the first, the third, up to the last interval. So you guys can see here when you want to calculate DL2 is going to be approximately equal to the square root of, because this is a square of the hypotenuse, is going to be here dxi, we square it, plus the square of dyi. So in fact, it's going to be here 2. I said I, but it's going to be 2 because I'm calculating I equal to 2. So be careful. Sorry, going to be 2 here. Because I'm just focusing here in the second interval. That's why just my I equal to 2. What I did here for the second subinterval will be repeated for all subintervals. And adding all these DLI, I'll get an approximation of the portion of the curve joining capital A and capital B. If you add all these small portions. Any question? Okay, let me know whenever you're done. So in the next page, so we'll see now how to get the length of the portion of the curve of F joining capital A and capital B. As I told you, we're going to approximate it by adding this elementary elementary length of this small portion. So we just want to take the portion P0, P1 plus P1, P2, and so on up to Pn minus 1 Pn. So let me know whenever you're done. Is it okay? All right, thank you. Can I erase this? All right, thank you. Now we can see the details here. As I said, this is exactly what I explained before, all the steps. So for the point PI, as I said before, the coordinates are XI and YI. All these points, we have n plus 1 point. These points are used to subdivide the portion of the curve joining A and B into small portions. And DLI is the length of each small portion. And as I told you, we approximate it by using the Pythagoras theorem when we create our rectangle and adding all these elementary length, DLI. As I told you, the reason here, so in fact, here what I did is just, I just took the, oops, what is it again? All right, so from the equation that I got, I just took here dxi out. Okay, I told you. So you guys see this is your dli. And from there, we can see, as I told you before in the previous slide, it means dli is equal to the square root of, because this was the square, we take the square root to get dx squared plus dyi squared. And this is just, for the portion of the curve joining pi minus 1 and pi. This is just for interval I. As I told you, we're going to repeat it for all of them. So that's why the total length going to be equal to the sum of all these DLI when I goes from 1 to n. Okay, so if you take DL1, going to be for the portion of the curve joining P0 and P1. DL2 going to be the portion of the curve joining the point P2 and P3, and so on. We repeat for all of that. That's why we have to add all these. We have to add all these elementary volumes. And from this, you guys can see you can take. So from here, when you take dxi out of the square root, so you will get square root of dxi, you square it, times 1 plus dyi. I just factor out the dxi. I'm going to take it out of the square root in the next step. And you square. Okay, this is exactly the same thing. If you put it back, the dxi inside the square brackets is going to be dxi squared times 1 here. You get the first term. And dxi squared times this second term, the dxi squared cancel out, and it remains only dyi squared. Now I'm going to factor out dxi. When you take it out, it becomes only dxi times square root of 1 plus dyi over dxi. and you replace it here to get the sum. That's what we did to get this part here. So this is the approximation. And when we're going to get the exact value, we have to calculate the limit when n goes to infinity. And such limit exists because this is a Riemann sum. And we've seen the limit of a Riemann sum when you guys have continuous function, the limit going to be equal to a number. So we did it at the, couple of weeks ago when we was doing, defining the definite integral. So, and that integral is exactly equal to integral from a to b square root of 1 plus dy over dx. And just keep in mind, dy over dx is a derivative of y with respect to x. In our case, this is equal to just f dash, because at the beginning, I said y equal to f of x. So dy by dx is going to be just f dash. This is exactly equal to f dash of x. So basically it means anytime you guys want to calculate the length joining the point AB, so you have to integrate from the x coordinate of the initial point to the x coordinate of the terminal point of square root of 1 plus the derivative of f with respect to x, and you square it. Just keep in mind here, A and B are the x coordinate of the extreme point. Sounds good? All right, thank you. So next we'll do, before doing an example, just want to give you another situation. Sometimes the function is not in terms of x. In that case, it means you cannot calculate dy by dx. You have to differentiate respect to y. For example, if your function is in terms of y, your dy by dx becomes dx by dy. And your integral gonna be in terms of y. And in this case, you don't have to take the x coordinate of the extreme point. You have to take the y coordinates of the extreme point, because your function is in terms of y. That's why you're integrating with respect to y. So that's what I mentioned here. Just keep in mind, in this case, the function is in terms of y. That's why we have to calculate the derivative with respect to y, and the whole will be in terms of y. That's why the integral going to be in terms of y. And in that case, the limit of your integral going to be the y coordinates of the extreme point. So back to our picture. So you guys can see here, if you integrate with respect to x, you have to integrate from a to b. That's the first formula. If you integrate with respect to y, you have to integrate from c to d. That's the last formula that I gave you. From c to d, if your function is in terms of y. So you have to integrate respect to the y values. So that's why I have to take the y coordinates of the extreme point in terms of x. So basically it means this is, the case where your function is in terms of x. In terms of y, you switch this part is dx over dy. And that's exactly what we have here. And we go from c to d because we use the y coordinates because we're integrating with respect to y. Is it okay? All right. So here I have two 24xy equal to x to the power 4 plus 48, and oops, the initial point here is this point 2 and 4 by 3, and this is the terminal point. This is the x coordinate for the terminal point, and here is the y coordinate for the starting point. This is my capital A, this is a x coordinate, and here is a y coordinate. Now, the formula that you guys have to use, so far we've seen two formulas. In fact, it's the same. It depends on just how the function is defined. So it means you first need to express your function either in terms of x or in terms of y. But in this case, it's not possible to express it in terms of y, because if you want to express your function in terms of y, you need to isolate your x. But it's not possible to isolate the x because you have x one side and the other side is going to be x to the power 4. What we can do here is just to isolate the y, and in this case, our function is going to be in terms of x. So from here, so we can isolate y, is going to be y equal to x to the power 4 plus 48 over 24x. And you guys see now, the function is 24. Now the function is expressed in terms of x. So it means when we apply the formula, we have to integrate with respect to x. And in this case, it means you have to take the x coordinates only of the extreme point. We don't use this one. If this function was in terms of y, the limit our integral gonna be 4 by 3 and 43 by 4. If your function was in terms of x, that's why we have to take the x coordinates in our integral. Okay?
So there will be 24x.
Yeah, 24x here, the bottom.
Yes.
Yeah. This is a 4. Is it okay? All right, now let's see how to solve it. All right. So here is our example. So we have 24xy equal to x to the power 4 plus 48. As I told you, we isolate the y. So we obtain y equal to x to the power 4 plus 48 by 24x. So we split it into quotients, and we'll get x to the power 4 over 24x. We simplify by x, it becomes x to the power 3 by 24. And the second term, which is equal to 48 by 24x, we're going to simplify by 24. It becomes 2 by x. And now we're ready to apply the formula, which is equal to integral from a to b. As I told you before, the reason why we consider here the x coordinate of the extreme point, because our function is in terms of x. That's why when we integrate, the limit of our integral gonna be the x coordinates. If the function was in terms of y, so we're gonna use the y coordinates of the extreme point. Now, the second term is a derivative. So we have to calculate the derivative of y with respect to x. So you differentiate the first term here, x cubed is gonna be 3x squared by 24. That's exactly what I got here. And I simplify by 3. So we'll get a 1 up and down, it becomes 8. And for the second term, 2 by x, when you calculate the derivative by using power rule, if you want, you can memorize the formula, or you can use the power rule. It's going to be negative 2 over x squared. This is the derivative of 2 by x. And to calculate this integral, I need first to expand this bracket. Okay, I'm going to let you write down this, and then next we'll see how to expand it. Which part? Yeah. You use the power rule, it becomes 3x squared. And down still equal to 24.
Sir, and y ds
Pardon?
and dy divide ds, and but I can see the ds.
Do you know what the meaning of dy by dx?
It means the derivative of dy, right?
No. Dy by dx means the derivative of y with respect to x. You don't have dx anymore.
Oh.
Dx. We've seen this notation, a couple of months ago.
Okay,
this
sir.
means you calculate the derivative of this function. Okay. It's what we call the Leibniz notation. So you did it in 1500 last semester. So y is equal to f of x. Okay. And this notation dy by dx, you use it many times when you was doing, the related rates problem in 1500. This means f dash. That's the meaning. This means dy doesn't mean derivative of y only. It means the derivative of y, but anytime you differentiate a function, the derivative is calculating with respect to something, another variable. Okay? And the derivative, they told you in 1500, just a small variation with respect to the independent variable. And the independent variable is x, and the dependent variable is y. Calculating the derivative of a function means how your function is changing with respect to x, with a small change in x, in the values of x. That's the meaning of the derivative. So this notation now means f dash only. That's why you cannot get the dx down. It's not dividing something. Dy doesn't mean just what we got here. Is it okay?
Okay, sir. Thank you.
So you calculate the derivative of this function. That's the meaning of this notation. All this is a derivative of this function. Any question? So from here now, when you calculate the derivative, the x cube over 24 to differentiate, this is same as calculating the derivative of 1 over 24 times x cubed. So when you differentiate it, as you know, you don't have to differentiate the constant 124. You don't differentiate it. You only differentiate the x cubed is going to be 3x squared. And that's what I got here. And now you simplify by 3, it becomes 1 by 8 times x squared. And that's what we got here. Is it okay? I simplify by 3. So next, as I said, I'm going to expand this bracket and to expand identity formula is going to be the square of x squared over 8 is going to be just x to the power 4 over 64 times this product. You multiply these two. Okay. So when you multiply these two, it's going to be just, 1 by 2, because you guys want to calculate here 2 times x squared over 8 times 2 over x squared. When you expand this part, so you will get first going to be x to the power 4 plus 4 plus this plus now 4 over x to the power 4. But from here, this term cancel out. So from here, you guys can see x you square it, and this x squared cancel out, and now it becomes 2. It becomes 2 times 2 going to be 4 over 8, but 4 over 8 is just equal to 1 over 2 here. And the last term here is just the square of the last term. Any question? Right. All right, so let's move on to the next page. As I said, these 3 terms are from the expansion of this by using a minus b squared. So next, you guys can calculate here the first term here, 1 and minus 1 over 2. It becomes 1 over 2. Okay, I'm just going to copy this second term and the fourth one. And I'm going to add, the first term, 1 minus 1 by 2, going to be 1 over 2. And that's exactly what we got here. It was 1 minus 1 over 2. It becomes 1 over 2. So this was the first second term. I just copied, and I copied the last term. And you guys can see this is a square based on the previous step. It's similar to the last step on the previous page, except here it was just minus. Now it's plus. It means this is the square of this bracket. Any question before I move to the next step? Pardon? Which one? It didn't. You didn't listen? I said I said here you have 1 minus 1 over 2. Yeah, it becomes 1 over 2. That's it. What do you mean by disappear? 1 minus 1 over 2, it's equal to. You cannot copy it again, cannot stay here because you add them. 1 minus 1 over 2 is equal to 1 over 2, right? Yeah. It becomes 1 over 2 here. Yeah. After that, you notice this is similar to this step to these 3 terms, except here it's minus now, but it becomes plus here. It's a plus instead of minus, right? And I know these three terms are obtained from the expansion of this. And you know the formula a minus b squared. Okay, so it means this is just the same thing. Instead of minus, it becomes a plus. I just use the what I from the previous step, and I realize this exactly what I got on the previous step, except it was here minus. But the three terms that I got in the previous step was obtained from the expansion of a square, and we know the formula of the square. That's why I just wrote it like that. If you expand it again, you will get exactly this. And this square integral going to be exactly equal to x squared by 8 plus 2 over x squared. And now we use the power rule for integral. So the antiderivative of x squared going to be x cubed by 3. But x cubed by 3 times 1 over 8 going to give us x cubed by 24. And the antiderivative of 2x squared going to be minus 2 over x by using power rule again, because the x squared, you can send it to the top. It becomes 2 times x to the power minus 2. And you use the power rule, it becomes a minus times x to the power minus 1. And you bring it down, it becomes over x. So next, you just want to substitute x by 3. It's going to be 3 to the power 3, going to be 27 by 24. And here when x equal to 3, 2 by 3. So the first bracket here is obtained when you substitute x by 3. And the second bracket when you substitute x by 2. And when you drop all brackets, so you will get just 27 by 24 units. And this is the length of the portion of the curve of f joining the 2 point. Any question? All right. So if there is no question, I'm going to move to the next section to calculate the arc length when we have a parametric curve. So in this case, we're going to use the same formula, but you have just to adapt it to our situation. So next, we suppose here now we have a parametric curve defined by these two equations, x equal to f of t and y equal to g of t when t is between alpha and beta. So in this case, you have to integrate with respect to t, because x and y both are in terms of t. And in this case, the integral becomes integral from alpha to beta, because in this case, t is between alpha and beta, given by the question here. And you calculate dx by dt, you square it, plus dy by dt squared. And this formula is exactly equal to the previous one. We just adapted to to our parametric equations. And what you have to use when you guys have a parametric curve defined by two equations. So next I'm going to give you two examples, so we'll see how to solve them. In the first example, this is my function f, and this is my function g of t, and t is between alpha and beta, means alpha equal to 0 and beta is equal to pi. So just keep in mind t equal to 0 correspond to a point, same for pi equal to 0, because we've seen for each value of p we have a corresponding value of x and y, which is going to be the coordinate of the point. All right, so let's solve the first example. All right, for the first example, just apply exactly what the formula says. I'm just gonna remind you here. The formula says it's gonna be integral for the arc length from alpha to beta. And we have the square root of the derivative of x with respect to the parameter t, and we square it. Plus now, so plus the derivative of y with respect to t, and we square it. Knowing x and y, so we square it here. And the integral is with respect to t, because under the square root, you guys will get a function in terms of t. And knowing x and y, so you guys calculate their derivative under the square root. So when we differentiate, okay. So this is, the derivative of x. You guys see the dash notation. So it means I'm just going to differentiate x and differentiate y. You square them. And when you differentiate x here by using chain rule, so you guys will get 2 cosine 2t is the derivative of sine 2t, and we square it. So when we differentiate cosine 2t, again by chain rule, so we'll get -2 sine of 2t, and we square it. So when we drop the brackets, so we'll get here 4, because we get 2, you squared, it's going to be 4 cosine square 2t. And the second bracket becomes 4 sine square 2t. And you guys can see here 4 is a common factor. I'm just going to factor out 4. So when you factor out 4, you guys will get cosine square 2t plus sine square 2t, and we know is equal to, oops, I'm going to check. All right. So here from this step, what I did is, you guys can see 4 is a common factor. I just took it out. Not out of the square root, just a factor out under the square root. And doing so, I'll get, I'm just going to show you here. So when you factor out here, so we'll get square root of 4 times cosine square of 2t plus sine square of 2t. And we know cosine square plus sine square is going to be equal to 1. And we know this bracket is in fact equal to 1. That's why we got this. And root of 4 going to be 2. So we integrate 2, going to be just 2x for the antiderivative. And we take it at 0 and at pi. Okay. Don't forget the formula. You have to differentiate before taking the square. That's what we did here. We differentiate first, and then we took the square. And the length of this is going to be 2 pi.
Sir, could you please zoom out?
Yeah. So let me know whenever you're done, and I will see the next example. All good? All right, thank you. All right, for the next example, again, we have a parametric curve defined by these two equations when t is between 0 and 3, the portion of the curve. Again, we have to integrate from 0 to 3 in this case and apply exactly what the formula says. You need to calculate the derivative of x and the derivative of y. All right, so I just repeat, our two equations, x and y in terms of t. And what the formula says, we integrate from 0 to 3 given by the questions, the limit of our integral. And for the first term under this is the derivative of x, as you can see, the dash sign, you square it. And the second bracket is the derivative of y, you square it. So now you differentiate term by term. So when you differentiate e to the power t, you still get e to the power t. But when you differentiate e to the power negative t by chain rule, it's going to be negative e to the power negative t. So we differentiate the second bracket here. First term is a constant, so we'll get 0. And you differentiate negative 2t, it becomes a negative 2. Now I'm going to drop the brackets and expand all these. When you expand it, e to the power t u squared, we have just used, a minus b squared. It's going to be a squared minus 2ab. When you multiply these two, it's going to be just e to the power 0. Because when you multiply them, it becomes e to the power t minus t. Going to be e to the power 0, which is equal to 1. That's why, we only got here 2. And you take the square of the second term here, it becomes e to the power negative. And the last term you square it, it becomes 4. And I'm going to calculate here this one, -2 plus 4. And doing so, it becomes just +2 because we have negative plus, we're going to be 2. And you guys notice here, these 3 terms under the square root is similar to this. And this is just, the square of this bracket. So it means this is also a square. So we have to take the same thing and just change this negative to positive sign because of this positive here. And now we're ready to calculate the integral. So the square root and the exponent to cancel out. And we'll get just, e to the power t minus plus e to the power -t. So the integral of e to the power t is equal to itself. That's exactly what we got here. But the integral of e to the power -t going to be -e to the power -t. And we have to take it at 0 and 3. So at 3, we get this bracket. But at 0 is going to be 0. Why? Because when t equal to 0, you guys will get here e to the power 0 minus e to the power -0. And it's going to be just 1 minus 1 in that case. That's why we got 0. And we're done. Any question? So you guys are done?
Yes, sir.
All right. So the next case is when you guys have a polar curve. So far we did, in the Cartesian coordinates, how to calculate the arc length. And here is, when we guys have a pyramid curve. And next we'll see, how to calculate the arc length of a polar curve. And same formula again. We suppose here we have a polar curve given by this equation r equal to f of theta. And theta is between these two values, a and b. Okay. So these are going to be in terms of theta in this case. And the formula becomes square root of r u squared plus the derivative of r respect to theta, and we integrate respect to theta. So in this case, you guys can also use the previous formula, dx by dt plus dy by dt, but it's going to be longer. So because in that case, you have to express x and y in terms of theta first, because you guys know x is going to be r cosine theta and y is r sine of theta, and r is right here given. And to save time, it's better to use this formula. Okay. So here is an example. And in this case, this is my f of theta, r equal to f of theta. But here, you know, the interval of integration is not given. We don't know a and b. And to find them, so the question asks us to sketch the curve in order to see exactly how to find the interval of integration. Just keep in mind, in this case, we want to get the length of the entire curve, not a portion of the curve. We want to get the entire curve. And as you know, when you want to go the entire curve, the theta is going from 0 to pi for the polar curve. And I just get the curve here. We already know how to sketch it. I just consider here theta equal to 0, theta equal to pi by 2, pi, 3 pi by 2, and 2 pi. That's all. When theta equal to 0, you substitute here. You will get cosine of 0 going to be 1. That's what I got here. When theta equal to pi by 2, so pi by 2 over 2 going to be pi by 4. And we know cosine of pi by 4 is root 2 over 2. We square it. So root over 2, you square it, it becomes 1 over 2. That's what we have here. This is 1 over 2. This is distance. And when theta equal to pi, so we'll get here pi by 2. The cosine of pi by 2 is 0. So it means we go to the pole. And when theta equal to 3 pi by 2, we substitute here by 3 pi by 2, it becomes a 3 pi by 4. And the cosine is going to be just, you know, minus root 2 over 2. You square it, it becomes 1 over 2. And at 2 pi, you substitute here theta by 2 pi, it becomes cosine pi. The 2 cancel out. But cosine pi is minus 1. You square it, it becomes 1. So return to the same point. And when you join all these 4 points, so we'll get the cardioid. And as you can see, as I told you before, since you know the question is good to get the entire curve, so we have to integrate from 0 to 2 pi. But from the picture, so you can say, okay, I don't need to integrate from 0 to 2 pi. That's why I gave you two formulas. You can use this one, just, you know, integrating from 0 to 2 pi, or you can say you don't need it because the curve is symmetric with respect to the horizontal axis. So it means the portion of the curve above the horizontal axis is exactly equal to the curve, the portion below. So it means it's going to be enough to calculate one of them, one of the two portions, and multiply. And that's what I said here. It's exactly calculating from 0 to pi up to here. You will get the half of the curve, and you multiply it by 2. Because from 0 to pi, you'll get the half. Now, be careful. I'm not saying it's always the case. Here, our curve is symmetric. That's why. Okay. Now, instead of using the first integral, I'm going to use this one. But at the end of the day, you will get the same solution if this one too. It's the same formula, except here, I just calculate the integral over this interval 0 to pi. And here, I'm going to take it from 0 to 2 pi and multiply by 2. Because from pi, I'll get just half of the curve. I multiply by 2, I'll get the entire curve. Now I'm going to take this one integral from 0 to pi and multiply it by 2. And we apply what the formula says. You take the square of r. R is right here. When you square it, it becomes cosine to the power of 4. That's what we got here. Because we square the cosine square. And second term under the square root, you have to differentiate r with respect to theta, and you take the square root. But when you differentiate r with respect to theta, so you have to use chain rule. Twice you did it becomes 2 cosine 2 theta to the power 1 times the derivative of cosine theta over 2. But cosine theta over 2, when you differentiate it, is going to be minus 1 over 2 sine theta over 2. And you take the square of all this. In fact, the bracket is all this, as you can see, from here up to here. No, up to here. So this is the bracket. So we have one bracket here, but the square is all this. That's what the formula says here. Now, I'm going to simplify by 2 first. And when it's, so it's going to be cosine square, and this minus sine theta over 2, because of the square, it becomes just sine square theta over 2. So basically, it means under the square root, so it means under the square root, what you got here is, I'm just gonna, so under the square root, you guys will get square root of cosine theta by 2 to the power 4 and plus cosine theta by 2 we square it because of this square here, and times, we already simplify the 2, so it's sine square of theta over. So this is exactly what we got from here. This part here. And now you guys can see cosine square is a common factor. I'm going to factor out the cosine square. So I'll get here cosine square of theta over 2 times cosine square of theta over 2. When you put it back, it becomes cosine to the power 4. And here, second term, when you take out, the cosine square, it remains the sine square. So we'll get here plus sine square of theta over 2. That's what I got here. And the bracket is just 1. And that's why we got the square root here of cosine square theta over 2. Is it okay? Any question? Guys, you let me know whenever you're done. Just keep in mind the second term under the square root is obtained when we apply the chain rule twice. All good?
Yes.
All right, let's move on. Now from here, I need to, remove the square root, but be careful. Just keep in mind the square root supposed to return as a positive number. As you know, when you calculate the square root of -2, what is this value? Square root of -2 square.
2.
2, not -2, because the square root always returns you a positive number. Now, how it becomes a positive? Because it's the absolute value of -2. And this is equal to 2. If you take the square root of 2 square, you still get the same thing, because it's just, 4. Root of 4 equal to 2. So we'll get again absolute value of 2, but it's already positive. The absolute value gonna returns you the same thing. Value always returns a positive number coming from here. So based on these two examples, this is just from how the square root is defined. If you calculate the square of any x, this is always equal to absolute value of x. Now, if x is positive, it's going to be the same thing. If x is negative, we have to add a negative sign in order to make it positive. So that's why here, so be careful. Anytime you guys have this situation, you take the absolute value. Don't just say the square root cancel the square here. It becomes just cosine theta. Okay, in this case, it's going to be the same, but not always. So we'll see why it's going to be the same. Okay. It already fixed. Yeah. Okay. Oops. Just gonna make some. So under the square root, it was theta over 2. And as I told you here, when you take the square root of cosine square, it becomes absolute value of cosine. Now to calculate the integral, I need to drop the absolute value. And to do so, I need to know the sign of cosine theta over 2. Is it positive or negative? Because if it's a positive, I'm just gonna write the same thing. If it's a negative, I'm gonna multiply it by -1 in order to make it positive. That's why I need to know it's a sign. But it's gonna be positive because of what I mentioned here. The reason is when you integrate from 0 to pi, it means the variable theta is the values, it's values between 0 and pi. And when theta is between 0 and pi, means theta by 2 going to be between 0 and pi by 2. So it means theta by 2 is in the first quarter So you multiply by -1 to make it positive. So for that reason, I'm just gonna integrate here. The cosine theta by 2 is gonna be 2 times sine theta over 2 by using the FTC. So you calculate at pi by 2 and at 0. But at pi by 2, sine is equal to 1 times 4 to get 4. But sine of 0 we know is equal to 0. So this is 0. And so half of the length is equal to 2, though the length of this curve is equal to 4. Any question? Is it okay?
Yes, sir.
Any question? All right, if there is no question, I'm gonna let you go. We already covered, the first topic, which of a solid of revolution.
Test 3 result.
This weekend. I'm
Okay,
still
sir.
marking. Yeah, so.
And sir, the test 3 are of 20%, right?
No, we just changed it. I don't remember again. It's already